Hi, I'd like to talk to you about the sampling distribution of the sampling proportion. So first let's start by talking or discussing what a sample proportion is. A sample proportion, usually denoted by p hat, is equal to the number of successes over the number of subjects or in that particular sample, or the size of that sample. So x equals the number of successes over the number of, or I should say it this way, the number of trials. You can put it that way if you like, or you could really think of this thing in the denominator as n equals the sample size. Okay, so it could be that you're asking, people's opinion, do they like vanilla ice cream or not, and you want to find a p hat, the proportion of people in the sample who say they like vanilla ice cream. It could be p hat equals the number of car parts that pass a particular type of test out of some sample size of 50 car parts, and you test to see how many of them are successful or do what they're supposed to do. Okay, and a sampling distribution would just mean this. It would mean that you kept pulling samples out of the population. So, for example, if we're talking about, we wanted to know the proportion of people in Jericho High School who liked ice cream, like vanilla ice cream, we could do the following. We can interview, say, 25 people, ask them, do you like ice cream, vanilla ice cream or not? And when we did that, we'd have our first p hat, whatever that is. Maybe it was, say, 11 out of 25, which is 0.44. And then we can put those people back into the population, do a new random sample, and then get a different group of 25 people. And maybe out of that group, we only get 10 out of 25 people saying, oh, I like vanilla ice cream, and then that's 0.4. All right, so if we continue in this fashion, we'd have many, many p hats. The collective list of all those p hats we would refer to as the sampling distribution of p hat. And we've already discussed about sampling distributions of means, and so now we're switching gears a little bit. We're talking about a sampling distribution of proportions, or sample proportions. All right, so what can we say about it? Well, what I'd like to do is concern ourselves with the following. Just to review, when it came to sample means, or the sampling distribution for sample proportions, we learned the following fact, that mu of x is equal to mu of x bar. And remember, x bar is the mean of the sampling distribution. And we learned that if you take the standard deviation of the population and divide by the rate of the sample size, you got this standard deviation of the sampling distribution. Additionally, we learned that if m was large enough, that, so for n large, now generally what we said was if n is greater or equal to 30, then that implied the central limit theorem tells us that the distribution of x bar is approximately normal. And we were really happy about that. It was normal with mean mu of x and standard deviation sigma of x over rad n. Or you can write this mu of x, and this is sigma of x bar. Okay, so that was really a nice thing. Central limit theorem is what told us that the distribution of x bar was normal, and we would love to have that for the sample distribution of sampling proportions, and we're going to get it. There's one more thing we need to mention. This standard deviation formula is really only safe to use if the population that you're looking at is at least 10 times the sample size. Okay? All right. So having said that, we can actually go through everything for the sample proportions. Okay? So it turns out that the mean of the p hats, the mu of p hats, is equal to just the population proportion. So if, in the case of the ice cream example, if the true proportion of people in Jericho High School or any high school that like vanilla ice cream is 43%, then we'd expect the means of all the p hats that we were discussing over here. After a while, the mean of all these p hats would be 43%. Okay. Now, there is a standard deviation for p hat, although this formula is less obvious. We'll show you where it comes from in a minute, but here's what the formula says. It says it's equal to the square root of p times 1 minus p over n. And again, you can only use this if the population you're examining is greater than or equal to 10 times your sample size. So I can tell you that the high school I was giving as an example, if n's 25, then I can tell you that the population would have to be greater than 250, which it is. If the population wasn't that big, then you can't use this and you can't do any of the math we're talking about now. Now, there is not a central limit theorem that tells us about the sampling distribution of the sample proportion. Instead, what we say is this. If n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then the distribution of p hat is approximately normal. Okay? And it's normal with mean p and standard deviation square root p 1 minus p over n. So you may ask, well, or you may think to yourself, hey, wait a minute, I feel like I've seen this before. This stuff, if n times p and n times minus p is greater than or equal to 10, then the distribution of something was approximately normal. And you've seen that before when it came to binomial random variables. So now what I'm going to do is I'm going to show you where these two formulas right here, where this formula and this formula come from. Okay, so we'll start with p hat. If we look at p hat is always the number of successes out of n trials. It's a proportion. X is counting the number of successes in n trials, and we're dividing by n the number of trials, and that's how we're making it into a proportion. Well, that's sort of telling us X is a binomial random variable. Okay, so if X is a binomial random variable, then what do we know about X? Well, if we just think about X for a minute, X is binomial with n and p, then we know that mu of X is equal to n times p, and these are formulas from the beginning of chapter 8, section 8.1 of your textbook. And we know the standard deviation of a binomial random variable is the square root of n p times 1 minus p. Okay, so now what we'll do is we'll just remember a few things we learned about random variables. Now we're interested in mu of p hat, but let's think about p hat for a minute. So if we go back up here and we look at this, we can write p hat another way. We can say p hat equals 1 over n times x. So what we can do is we can say p hat, mu of p hat is just mu of 1 over n times x. But that's 1 over n times mu of x, and that's because of our rule of means from random variables. Well, mu of x is n times p, so we get 1 over n times p. The n's cancel, and we get p. So there's our first fact. That's why mu of p hat equals p. All right. The standard deviation of p hat would equal the standard deviation of 1 over n times x. And what did we learn? Well, we learned a while ago that to get the standard deviation of ax plus b, you take the absolute value of a and you multiply it by the standard deviation of x. So that's something we learned about random variables. We can do that here. This becomes the absolute value of 1 over n times the standard deviation of x. But the standard deviation of x, by our definition above, is this, right there. So this becomes times the square root of np 1 minus p. We can finish that now because this is equal to the following. Now, if you want to bring 1 over n squared inside the radical, you have to square it. So it becomes 1 over n quantity squared times np 1 minus p. Well, that's equal to the square root of 1 over n squared times np 1 minus p. And then we get that formula we had on the other page. This is the square root. If you look at one of these n's, cancels with that, you get p times 1 minus p over n. So that's sigma of p hat. Important thing for you to know is this stuff on this page. This turns out to be the most important thing to remember about sampling distributions for sample means and sample proportions. Thanks for watching.